myself first. Hello, everyone. My name is Shuchen Zhao from UC Santa Cruz. So I'm happy to present my job market paper, Taking Turns in Continuous Time Battle of Sexes. So let's get started. Okay, so as you might all know, Battle of Sexes capture the real-world tension of coordination when people have mixed motives with many kinds of applications. So thinking of a 2x2 biometrics framework, there will be two players with two pure Nash equilibrium. So different players will prefer different pure Nash equilibrium, and which cause two different types of mixed coordination. Either both players choose their own preferred equilibrium, or they choose the other player's preferred equilibrium. So as you can see, the cartoon below shows actually a very typical idea when both players choose to benefit the others, but eventually they mismatch. When the game is played repeatedly, then the players may take turns among the pure Nash and alternate among them. And it's been supported by many theories and experimental results. Also, nowadays we face such problems more and more in the online environments. So for example, thinking about two different teams, they want to coordinate their demand for two different servers. One is fast, the other one is slow. So of course, all of them want the fast server, but accessing it together will lower the speed for everyone, which is not good. So they need to coordinate their demands. One use the fast one, the other use the slow one. If that's the repeated interaction, and they can take turns, of course, to use the fast server. That is actually very similar to a traditional application of the Battle of Sexes, but what's different in the online environment is that people can actually interact and change actions in real time, which leads us to my research question: how does this continuous time environment affect the coordination in this repeated Battle of Sexes? Should people embrace the new technology to speed up their interaction, or should they slow down and try to discretize their choices? The answer is actually ambiguous. So on one hand, from the previous literature, it suggests that people converge faster to equilibrium in the continuous time, which may improve the efficiency. On the other hand, however, the alternation might be more difficult in continuous time. So people need not only to coordinate at the order of the alternation, but they also need to coordinate at how long to stay at each Nash equilibrium, where in the discrete time, the latter one is not a problem. So what I did is that I compare human subjects' behavior in Battle of Sexes in two time environments by answering the three major research questions. First, is there any treatment effect of the time environment? Do continuous time interactions facilitate coordination in Battle of Sexes? Secondly, if there exist some differences, what may cause the differences between the two time environments? Thirdly, what type of equilibrium do subjects eventually converge to in the continuous time? By answering those three research questions, this paper contributes to the literature from the following three perspectives. First, it provides new evidence to advance the theory of the continuous time game in general. Secondly, since players can move asynchronously between the entire continuous time, it offers a new perspective to explain what really motivates people to take turns. Thirdly, as I mentioned before, it suggests practical solutions to the online applications. So before we walk into the design and experiment, let's take a quick look at the summary of the results. First of all, I found that people behave quite differently in those two time environments. On one hand, in continuous time, people converge to their first Nash and deviate from mismatch faster than what they do in the discrete time. But on the other hand, the continuous time environment also undermines players' subsequent ability to maintain such coordination in the equilibrium pause, and it also slows down the learning in general. Given those two contradictory forces, they offset each other, and eventually the treatment effect of continuous time becomes insignificant. Also about the dynamics in continuous time, I found that although the transitions are quite diverse and unstable, it is actually mainly motivated by the disadvantaged players, the player who earns a lower payoff at Nash. So you're going to see all of those results in the following slides. Okay, so how do I design my experiment? I use a 2x3 full factorial design with two time environments between subjects and also three payoff matrices for robustness check within subjects. Data are collected from 84 subjects and based on O3 and ORC. In each session, subjects are randomly paid by one of the 12 super games followed after 3 practice games. Each super game lasts for 2 minutes, and the subjects are randomly rematched between super games, but they are matched with the same partner in each super game. the way they play each super game is depends on the timing environment they experience. So this is the UI of the continuous sum treatment. So as you can see on the left-hand side, it shows the payoff matrix and also the choice they can make. On the right-hand side, it shows the current history of the super game. So subject play under the full history of the game. They can see both their choices and payoff, as well as their opponents' choices and payoff. So in discrete time, each super game will be equally divided into 20 periods. So they just play a traditional repeated game. And note that they cannot see what the other player is choosing right now, but they can only see what the other player has chosen in the previous periods. In a continuous time, however, everything will move in real time, both for actions and for payoffs. And the latency is about 50 milliseconds, which is well below the fastest response time of human subjects. So I believe they will believe themselves playing in the real time. And also, the data are recorded twice every second. And here are the three matrices I use. So those are for robustness check. The name BUSX, that X actually refers to the differences in payoff at Nash. So for example, if you take a look at the top left one, so 1.4 is actually 400 divided by 280. So to check the order effects, I have two different game sequences between subjects. In both sequences, they play all three matrices in a rotating manner. The only difference is that in the first sequence one, they first start with the BUS 1.4. And it is predicted by the previous literature that people are more likely to coordinate in the BUS 1.4, the easy case. And in the sequence two, they play the game in a similar way, but they start with a more difficult game. Okay, so let's go back to my results. The first question is about the treatment effects. Basically, those continuous interactions facilitate coordination in battle of sexes. And you can see that from the panel A and B in the first table. So you can compare the time environments by column and payoff matrices by row. And the number here shows the coordination rate, which is the average fraction of time that a pair stay at either Nash. As you can see, surprisingly, people are actually more likely to coordinate in the discrete time than continuous time. And about the predictions of the payoff matrices, that's quite similar to the theory predictions. People are more likely to coordinate when the asymmetry is low. However, and also in panel B, we can see that there's slightly different coordination rate in two different sequences. People are more likely to coordinate in sequence one rather than in sequence two. However, as you can see, none of the treatment effect is statistically significant. So which basically leads us to the first result as follows. We can find that both the treatment effects of time environment and the matrices are weak and insignificant. But does it mean that people play similarly in those two games? The answer is, of course, no. So I'll check that from the two following perspectives. First, as I mentioned before, it is actually more difficult by design for people to take turns in the continuous sum because they need to focus on a multi-dimensional of coordination. So let's check how often do they converge to alternating dynamics. And since it have some difficulty in the coordination, does that affect the learning in general? But to answer the first question, let's first take a look at the way I define a alternating dynamics. So you can see from this figure, the x-axis shows the total fraction of time people spend at Nash, either pure Nash. The y-axis shows the difference in time people spend at 2 Nash. So for example, if a pair is located at 1, 0, that means that they spend their entire time at Nash, and also the difference is 0. So they split equally between two pure Nash. But if they move to 1, 1, then we see they spend their entire time at Nash, but they only focus on one Nash. They prefer one Nash to the other one. So the way I define a alternating pair is when subjects coordinate at over 80% of time, and also that the time difference between the two pure Nash is less than 20% of time. If they satisfy the first criterion, but fail to do the second one, then we'll say they prefer one Nash to the other one, but they still coordinate. Note that these criterions are robusted. I changed the first one from 60% to 90%, the second one from 0% to 30%. All the combinations are going to see does not really affect the result I'm going to show you in the next slides. So what does the result look like? I used two different data sets. In panel A, I only use the data from the last second half of the game. So from period 11 to period 20, after they get some experience with the other player. In panel B, I use the entire data set. And the number here shows how what fraction of pairs can be classified into playing alternating, or they only stay at one Nash. So as you can see, people are more likely to take turns in the discrete time. But at the same time, they are more likely to stay at one Nash in the continuous time than in discrete time. And all the differences are actually statistically significant in both panels. So we can see that it's actually more difficult for them to take turns in the continuous time than in discrete time. Does that affect the learning in general? So here you can see the average coordination rate within supergames. So that is how they learn within the game. So as you can see, the blue curve, the continuous time average coordination rate, although people start with a higher coordination rate, it does not really improve over time, even slightly decreased. But for the discrete time, the red curve, although it starts with a relatively lower coordination rate, it catch up really quickly and eventually go beyond the curve of the continuous time. So people learn in discrete time, but they do not learn in continuous time. This is also true when they learn between super games. So I split the 12 games into two different blocks. Note that they play the 3 matrices twice in each block. So as you can see, if we compare the coordination rate in the first block to the second block, they do not really learn in continuous time, but they can carry what they learn from the previous game even after they switch partners in the discrete time. The differences are quite significant. And all 3 results lead us to the second result. Basically, it's more difficult for subjects to learn alternating dynamics in the continuous time than in discrete time. And that difficulty actually slows down the learning in general, both between supergames and within each supergame. But does it mean that continuous time game is strictly dominated by the discrete time? Note that in the previous literature, we found that in general, people respond faster in continuous time. Is that true in my experiment? So I'm going to use 2 different figures to show you how that works. This is the cumulative distribution function of the time at which pairs first reach either pure Nash. So for each pair, I take a look at the timing when they first touch the Nash. But notice that in the discrete time, that the minimum number is 1. And in continuous time, that number is 0.16. So by design, people should respond faster to Nash in the continuous time. And that is exactly what they did. We can see that the blue CDF is well above the red CDF, which means that on average speaking, they converge to their first Nash faster in continuous time than in discrete time. Although you can see that by design, at least people make use of the benefit of the continuous time. Similarly, this is the CDF of the average duration during which subjects stay at mismatches. So as you can see, still the blue curve is well above the red curve, which shows that people deviate from mismatch position faster in continuous time than in discrete time. Although it still could be by design, at least people make use of this benefit of the continuous time, which gave us the third result that the subject respond faster in continuous time than they can do in discrete time, which kind of like a benefit for the continuous time environment. And that actually answers the first 2 research questions. So next, how do subjects really interact in continuous time? So I'll take a look at this from the following 2 perspectives. First, how do they move between action profiles? How do they transit from one choice to the other one? Secondly, how long do they stay at Nash? In the discrete time, if they take turns by 1 period, the number could be 1, but continuous time, they don't have such a reference point. So for the first question, we mainly focus on the 3 types of transitions. So if the transitions between profiles are motivated by the advantage players in continuous time, then we can see the following dynamics. So for example, if they start at AA, which is the Nash preferred by the role player, then the role player earns a higher payoff. So the role player will switch first, and then the column player best respond. So that move from AA through BA to BB. Similarly, if they start with BB, then the column player will switch first because this dynamic is actually led by the advantage players. And that's the transitions mostly happen between the Nash to the BA mismatch. But if the transitions are motivated by the player who has a lower payoff, however, if they're at AA, then the column player moves first. So they from AA to AB, then to BB. Similarly, if they start with BB, then they also go to AA through AB mismatch. Also, if one player led the entire transition, which may call strategic teaching, then the game will go in either counterclockwise cycles or clockwise cycles like this. So let's take a look at the transition probability matrices to see how that works. The red box basically shows in both panel A and panel B, basically shows when people transfer from a mismatch to a Nash. So as you can see, although the probability look very similar, the number of transitions that come from a B mismatch is much higher than the number of transition from a BA mismatch. So we can see that people are more likely to go to Nash from a B mismatch than from BA mismatch. Similarly, if you look at the blue boxes, you'll see that people are more likely to deviate from Nash to an AB mismatch. So the idea is that if you combine those two results, you see that the most frequently played transitions are actually from AB mismatch, where both players prefer their own preferred equilibrium and to Nash equilibrium. Also, second question is, how long do they on average stay at Nash? Here is the CDF of the duration during which subjects stay at Nash. As you can see, for the discrete time, we have a very strong pattern of the one period alternation. So people stay at Nash, either Nash for one period, and they switch to somewhere else. But for the continuous time, that duration are quite diverse and unstable. They can vary from 1 second to 20 seconds. And clearly you can see that from the CDF map. If we combine those two results, the direction of their movement and how long they stay at Nash, you see the following result, number 4. First of all, the data reveals a very clear alternating pattern in the discrete time, but the pattern in continuous time are quite diverse and unstable. But what we can find something common is that the most frequently transitions are between AB and Nash equilibrium, which supports the dynamics motivated by the disadvantaged players. And that's everything I got. So to conclude my paper, basically, although the overall effect is insignificant, subjects behave quite differently in two time environments. And either time environment has their own advantages. Also, the dynamic patterns in continuous time are quite diverse, but we can find something common is that the transitions are typically led by the disadvantaged subjects. Speaking of the practical implication, I can see a good way to solve the problem is actually combining the both time environments. So they can try to figure out how they alternate in the continuous time, but if they can go to the discrete time to maintain such coordination, that will be the best for the teams. And also that will be using the benefit of both time environment. Although I'm not sure how that could work in the real world, that is a possible solution for such problems. Secondly, in general, theoretically speaking, we found that the continuous time interactions may harm efficiency when players need to switch between multiple Nash equilibria in the equilibrium path, which is actually quite different from the predictions we studied in the previous literature. So let's say for my presentation, feel free to email me or go to my website for more of my research, and I'm happy to answer all the questions you have. And thank you for listening, and I'm looking forward to the discussion.